Good morning, everyone. So the cue for us was to get on stage when the music faded, and we got on stage and the next song started. So we were a little early, but good morning. It's great to have you all here. I hope you're having a great reInvent. Hope you're having a lot of useful learnings. Thank you for joining us today for this session on inner workings of Amazon EKS. My name is Vipin Mohan. I'm a principal product manager on the Amazon EKS team, and I'm joined by my colleague, Vipul Sabaya. He's a senior software development manager on Amazon EKS as well, so we work very closely with each other. So Kubernetes is a great way to run containers at scale. It's amazing how Kubernetes works, but there is a lot that goes on to managing Kubernetes. And all of that time, energy, and effort that you spend to manage Kubernetes is time you're taking away from delivering value and delighting your end customers. So in this session, we will give you a peek under the hood into how we operate Kubernetes with a managed service in Amazon EKS for you. So we'll give you an overview of how we deliver high availability, reliability, give you a secure environment for running your business critical applications, and give you resiliency and the confidence for you to run your business applications and offload the undifferentiated heavy lifting to us. So in terms of our agenda for today, we'll start off with a quick introduction into what is Amazon EKS, and we'll talk about why you should be using Amazon EKS for your Kubernetes applications. I'll also go over some of the use cases that our customers have told us for what they use EKS for. We'll also spend some time on Kubernetes versions and upgrades. I can see some heads nodding over here. So upgrades in Kubernetes are complex. So we'll talk about how EKS helps you with upgrades. And then we'll start peeling the onion and dive deeper into the EKS architecture. So I'll hand it off to Vipul. And we'll discuss how EKS scales to respond to the needs of your business applications, scaling up and scaling down, as well as how we deliver resiliency, how do we respond to data center incidents. We'll give you some best practices and some pointers on where you could follow up in future, as well as close out with a wrap-up and summary. So let's do a quick poll. I believe there's a simulcast room as well, but we'll do a show of hands here for this room and get a sense. So I'd like to know at what stage are you in your Kubernetes journey? So we have three options. I'll go over them one by one, and we'll do a show of hands. So if you are somebody who's just getting started, or your organization is interested in Kubernetes, you're just evaluating Kubernetes, let's do a show of hands. Okay. That's about, I think, 10, 20% of the room, I would say. If you are somebody who is getting knee-deep into Kubernetes, you're starting to run test workloads, maybe even have a handful of production workloads, let's do a show of hands. Okay, that's a slightly bigger number, about 40%. And lastly, if you have multiple production workloads on EKS and you're an expert in Kubernetes, let's do that. Oh yeah, that's the majority. That's like 50% of the room. Great. Awesome. So I'm hoping all of you have something to take away from the session today. So a quick introduction about Amazon EKS. So what is EKS? And I'll start by a quick overview of Kubernetes. Kubernetes is container orchestration software. It's open source, and it allows you or enables you to deploy your containerized applications and run your workloads at any scale. EKS runs vanilla Kubernetes under the hood. What that means is we do not fork the upstream code base. EKS is upstream conformance certified. And what that means is EKS passes all of the upstream conformance tests. And we apply and backport all of the security fixes that give you the peace of mind of running a secure Kubernetes environment with EKS. At any given point of time, EKS supports up to 6 versions of Kubernetes. We actually increased that in the past few months. It used to be 4 versions in the past, and now we support up to 6 versions. We'll talk more about that. EKS gives you a managed experience for running a performant and reliable, secure Kubernetes environment. And our goal and mission with EKS is to make Kubernetes operations and management simple and boring so that you can focus on delivering value to your end customers. So why Amazon EKS? So Kubernetes simplifies the deployment and management of containerized applications. But managing Kubernetes at scale is hard. So you need expertise and you need to staff teams to actually understand the overall Kubernetes architecture, how would you use Kubernetes in your environments, and also to deploy and manage Kubernetes applications on a scale that fits your needs. All of this is time spent away from delivering value to your end customers. Now, what are some of the challenges with running Kubernetes at scale? So firstly, the scalability aspect. So scaling a Kubernetes cluster efficiently while maintaining high availability and performance is a non-trivial task. So you need to ensure that your cluster can scale seamlessly to meet the varying needs of your business-critical applications. Then there's the aspect of security risks. So Kubernetes is open source software, and what that means is, there could be security vulnerabilities in Kubernetes. And the Kubernetes community, and we engage with the community as well to patch those security issues and security vulnerabilities. But you need to consume those fixes and apply those security fixes to your Kubernetes components if you are self-managing your Kubernetes cluster. There's also the angle of the complexity and learning curve. I touched upon this briefly. So when you want to manage your own Kubernetes control plane, you need to set up teams with expertise in Kubernetes to not just manage the control plane, but also to handle the operations. You need to set up monitoring. You need to set up alerts. How do you respond to scaling events? And all of this demands a steep learning curve, which can be time-consuming for your business. About the operational overhead, self-managing Kubernetes can pose significant operational overhead for your teams. And you need to dedicate resources and time for the continuous operations and management of Kubernetes. And when you are managing your Kubernetes clusters, you also need to take into account how do you deliver high availability and have disaster recovery systems in place. So ensuring that you need to have a disaster recovery plan, you need to think through how high availability would be achieved in your environments. All of that is a pretty involved effort and again takes time away from your business critical applications. So our core tenets tie into some of the topics that we talked in the previous slide. Security is job zero at AWS, and that applies to EKS as well. So our primary goal is to ensure that you're running your applications in a secure environment. EKS is built for production. So what that means is we are delivering a managed service that you can use to run production and mission-critical workloads. We have customers across healthcare, manufacturing, financial services who are running mission-critical workloads on EKS. About speed, scale, and reliability. So there's a few ways to think about this. One is how does the EKS infrastructure itself respond to your needs? So if you have a sudden burst in demand for your application, how does the control plane scale to actually meet those needs? How do we deliver an experience for your end customers with the minimum latency as possible? It also speaks to how quickly we respond to the community. So we are engaged with the upstream community. For example, we're part of the security committee. We have leadership roles in different working groups as well. And anytime there's a security vulnerability, we get engaged. And a lot of the times, you see those fixes even before they're public knowledge. EKS is upstream conformant, and we are committed to delivering the latest versions of the software with EKS and Kubernetes. And we also want to help you optimize compute. So at the end of the day, your applications are running on compute instances. But you need to figure out the right resources on your compute instance in terms of CPU and memory for running your applications. You could over-provision, but that would mean you're paying more without actually taking advantage of the entire resources in that particular instance. So we are coming up with ways by which you can optimize compute. So what are customers building on EKS? So we have customers using EKS across a variety of industries and verticals, all the way from manufacturing, healthcare, financial services, even three-letter government agencies are using EKS for various use cases. Some of them are legacy app modernization. So these are customers who are moving applications from on-prem over to the cloud. And these could be monolithic applications that they're modernizing and breaking down into microservices. And as they're doing that, they're choosing EKS to run their containerized workloads. AI/ML, I'm guessing most folks in this room have heard something about AI/ML this week. AI/ML has been a major focus for EKS and our customers in the past 12 to 15 months. And some use cases are autonomous vehicles. Customers use EKS to run object tracking and like computer vision in robotics, for example. And if you think about any AI/ML use case, there's going to be the aspect of modeling, training, and inference. So you first build a model, you train the model with some data, and then you derive inferences from that model. So we have customers using EKS across all of these applications and use cases. Data processing is another common use case that we've seen customers use EKS for. Think about like streaming use cases or heavy analytics use cases. It could be like financial services or healthcare, where there's a lot of data that needs to be processed. A lot of backends. So most of you have smartphones, and the likelihood is that at least one or more of your applications running on your smartphone are using EKS as a backend. It also applies in IoT, Internet of Things use cases. And web applications have been a very common use case right from the start of EKS, both for simple static websites as well as for complex dynamic websites. So when we launched EKS a little more than 5 years ago, EKS was the managed service in the cloud, and that still continues to be the case. But many of our customers told us that they have use cases wherein they cannot use the cloud for running their applications. Some customers told us that, hey, I have government regulations that determine where I can run my workload, like which geographies. And then there's like data sovereignty needs for which customers would want to run EKS closer to their geography. So we announced EKS for local zones a few years ago. So local zones is basically AWS infrastructure available closer to your geography. AWS Wavelength is a similar use case, but it's more focused on 5G and telco use cases. So these are use cases wherein the entire the application does not leave the network of the communication service provider. AWS Outposts, for those of you who are not aware, Outposts is AWS managed hardware. So you can have a set of server racks in your office or in your data center, and these are compute racks. You can run EKS on those racks. The hardware is managed by AWS, and you can run EKS on your Outpost instances. And lastly, like there were customers who told us that they have long-term data center leases that are not going to expire anytime soon, but they still want to modernize their applications where they are. So EKS Anywhere is the open source solution that we have for running Kubernetes on-prem. And the common theme here is consistency. So no matter where you're running EKS, you get the same set of bits, Kubernetes bits, and the same tooling for running your Kubernetes clusters. And when when you're ready, you're always free to move across different environments. So AWS has a global reach across different geographies, And EKS is available across 30 commercial regions. We added support for 5 commercial regions this year in Zurich, Hyderabad, Melbourne, Tel Aviv, and Spain. We have more regions coming. We're constantly building new regions, and we want to make EKS available in all of those regions. Besides that, you can see in that list, EKS has, you can run EKS in geographies across the Americas, Europe and Middle East, Asia Pacific, Africa, and China. And a lot of our customers, especially the government agencies, run EKS in GovCloud regions. How many of you have had issues with upgrades in Kubernetes in general? Let's do a show of hands. Yeah, that's a common topic. We've heard a lot from our customers, and a few common themes we heard from our customers were that you wanted to see consistency in versions that EKS supports. And we've delivered that this year. I'm super excited to say that as of now, we are caught up on all upstream Kubernetes versions. Up to 1.28, Kubernetes 1.28 has been available on EKS. 1.29 is planned for launch next week, December 5th, I believe, by the community. And we've been plugged in some of those 1.29 efforts for weeks, if not months in advance. With upgrades, you told us that there's a lot of complexity around upgrading your Kubernetes clusters. You need to dedicate resources for upgrades on an ongoing basis. And there's always conflicting priorities, and you need to choose between upgrades and your business priorities. And we feel that should be a slam dunk choice. Business priorities should always win over for you. And the release cadence, like the upstream community releases a new version every 4 months, and that's a pretty fast clip. So the way we've been responding to you, especially some of the things that we've announced this year, is we've been consistent with version launches. We've launched quite a few versions this year in EKS. 1.28 has been the latest. We've also announced something called extended support. I'll spend some time talking about that. We're announcing a feature very soon on pre-flight checks that will allow you to, or give you an idea about what APIs have been deprecated in a future Kubernetes version, even before you click the upgrade button. So the idea is that you get the confidence of performing an upgrade before you actually go through the entire process and figure out something is going to break. And we have more on the roadmap. We'll talk about that later. And with the upstream launches, there has been a discussion around long-term support, LTS. We are engaged in those working groups. We are co-chair. We have both product and engineering presence in that working group. So to quickly summarize, EKS supports versions from 1.23 to 1.28 today. 1.24 to 2.8 is in standard support, and extended support is something we announced new, and 1.23 is currently in extended support, and every single version going forward will get extended support. We have ended support for Kubernetes versions until 1.22. So extended support for Amazon EKS was something we announced in October this year. The upstream community supports a Kubernetes version for anywhere from 12 to 14 months. So it's 12 months of full support and then 2 months of patch support. What we've done is to extend that to 26 months for all of our EKS customers. So you get the 14 months of standard support plus 12 months of security patching for the control plane components, for the default add-ons, and for all of the armies. And it's available in free preview right now for 1.23. And it will be available for every future version of Kubernetes. And we're planning a GA of this feature in early 2024. There will be a pricing component associated with this for extended support, and those details will be available when we go GA. So to set the stage for the EKS architecture, EKS is a regional service. So there's a regional endpoint by which you would access your Kubernetes cluster. And the orange box that you see is the EKS interface. It's the EKS API. So you would access the EKS APIs, the orange box using the EKS APIs. And under the hood, we run vanilla Kubernetes. And once your cluster is up and running, all of the kubectl commands are available to you. You can use the Kubernetes APIs in your cluster. And we're running the same API server, kube controller manager, kube scheduler that you're familiar with upstream. And once you have your Kubernetes cluster running, you can integrate with a ton of AWS services, could be DynamoDB, EMR, IAM, or you could also take advantage of any open source software that's available, like Prometheus and Grafana are something we've seen very commonly used. So any open source software that's compatible with Kubernetes will run seamlessly with EKS because EKS is using vanilla Kubernetes under the hood. So I'll hand it over to Vipul to dive deeper into the EKS architecture.
All right, thanks, Vipin. So yeah, we're going to go a little bit deeper now and talk about how EKS works, how we operate Kubernetes for you, and hopefully give you some insights into various aspects of the service that you may not be aware of. So let's start off with the control plane architecture. So the Kubernetes control plane is fully managed by AWS. It's zonally redundant, which means that we have API servers in a minimum of 2 zones and etcd in 3 zones. Each one of these instances is in a private VPC, so you actually get VPC level isolation. We have an NLB, which is used for the public endpoint to the cluster. And the traffic within the NLB is actually isolated to the zone. So there is no cross-zone impact or anything like that when traffic enters a zone. So on top of this, we have a 99.95% SLA, 24/7 support. And I think the most important thing is the fact that EKS manages etcd for you. This is probably the most complicated thing to operate if you were doing this on your own. The data plane, this is where your applications run. These live in the customer account in the customer VPC. So initially we started off with self-managed nodes. This is where you spin up a worker node. That worker node joins the cluster, and then Kubernetes can schedule applications onto that node. We provide EKS optimized AMIs. When you spin up an instance with this AMI, that instance will join the cluster. This is still supported today, but what this means is you manage the complexity of doing the upgrade, cordoning and draining the nodes, evicting pods, things like that. We then launched EKS managed node groups. This is still where capacity exists in your account, in your VPC. It belongs to an ASG, but EKS takes care of some of the heavy lifting of upgrading, gracefully terminating the pods on a node and then moving them to another node, things like that. We also added a serverless option with Fargate. So Fargate is a AWS managed compute. It's fully managed by us. All you have to do is annotate a pod and say that I want this pod to land in Fargate. And today the model with Fargate is a single pod per node. So whenever you schedule a pod to Fargate, we actually spin up a node behind the scenes and schedule that pod on that node. And finally, we built Carpenter. So this is our version of a next-gen autoscaler. Carpenter is open source. We recently donated that to the CNCF. It gives you the flexibility of choosing the right instance types for your workload, whether it's an on-demand instance, a spot instance, or something else. It also helps you reduce costs. What it's actually doing is rebalancing your containers. So if there's holes in your worker nodes, it'll try to bin pack as much as it can and give you the ability to remove those nodes. So you don't have to go pay for just over provisioning. Carpenter also gives you an option to automatically replace your nodes. So in the event, like if you have a requirement which most of us probably do, where you need to do patching of the control plane or of the worker node, Carpenter will automatically recycle these so that the OS patching is taken care of for you. Okay, so now let's talk about how this architecture has led to better resiliency for us. So we spoke about zonal redundancy, that we have API servers, etcd, across multiple AZs. What we have, we all know this, that AZs do go down, and our goal is that a single zone going down should have zero impact on the cluster. And so what are we doing about this? How do we achieve that? I want to walk us through that a little bit. So over several years of operating EKS, we've kind of come to the conclusion that zonal failures are complicated. In practice, they're weird because they vary based on how they impact the capacity in a given region. So like an AZ may be fully down if it's on fire or something, or it might be partially down if there's a network disruption between some racks within the AZ. This could manifest as maybe increased latencies or reduced throughput, things that don't necessarily mean that it's a complete failure. So there's a lot of these different failure modes that may or may not cause impact to a cluster. So we have to reason about this. So we've actually, we've gathered a ton of experience in the past decade. Every time there's a failure, we dive deep, we dissect it, we analyze what exactly happened, what we could do to minimize the failure, and we've started to use those learnings to effectively give you a more reliable Kubernetes experience. So what we've implemented is deterministic AZ resiliency. What does this mean? What we're trying to do is no matter what type of failure mode we have with an AZ, we want to give you a deterministic outcome. And by that, what we mean is a seamless API experience where it's not just about the uptime, but even performance, things like latency and things that you would care about should continue to behave the same way as if there was no failure. We also want to provide no disruption or delays to any of the controller workflows in Kubernetes. So what do we do? In practice, the first thing we do is we pause all updates. So our goal is to retain existing capacity. We move all the traffic to the API servers from the unhealthy AZ to the healthy AZ. And this is not just client traffic coming from the outside. It's also long-running connections, watches, exec proxy, all these things that are supported by the Kubernetes API. These things are no longer going to the unhealthy AZ. We move the leader for all the backend controllers to a healthy AZ because we don't know if that leader, is a leader in a bad AZ, if it's going to be able to perform the operation that we need. We also move the etcd leader from the bad AZ to a good AZ. And we just want to ensure that all writes are not impacted if a leader was in the bad AZ. So we're working on bringing some of these capabilities to your applications as well. So things that are running on your worker nodes, we're going to be introducing some APIs where you can say, I want to evacuate my applications from a zone. That's going to be available sometime next year. So, okay. So what I want to demonstrate here is kind of things that we've implemented and how that's shown us the fact that we're doing it correctly, at least. So our biggest priority during a failure is what we call static stability. So in the event that there's an outage, our goal is to make sure existing clusters are not impacted. And by that, we mean they're statically stable. This requires us to look at pretty much all of our dependencies and architect around their failure modes. So we don't wait for an AZ outage to happen. We simulate them in production. We inject different types of failure modes, network outages. We prevent calls to dependency services. And then we also, let me scroll down here. Yeah, so health check failures, packet drops, various modes of failures to ensure that we are actually redundant and able to fail away from a zone. So more recently, as I think most of us probably know, we had an outage in US East 1 on 9/28. This was a zonal event. It was the classic gray failure where not the entire zone was impacted, it was only some racks within the zone, and even that was a partial rack failure within that zone. During this event, we did the root cause, we dissected our performance in that event, and we mitigated impact in our largest region. Customers didn't see impact. This is for hundreds of thousands of cluster in our largest region. Okay, so let's move on to the scalability of the control plane. So EKS automatically scales your cluster to provide you a right-sized control plane. We're consistently looking at signals such as memory, CPU, node count. We're looking at etcd signals. Once we get an aggregate of all these, we determine what the maximum value should be, and we scale your cluster to that max. It takes approximately 10 minutes to scale the cluster, and it depends on the exact type of operation that's happening. So if etcd needs to be scaled, or if it's just the API server that needs to be scaled, we do them independently, so it's not like you have to actually think about which one is getting scaled. We scale it vertically, and we're adding support for horizontal scaling as well. As part of the scaling operation, one of the things we also do is we tune various parameters of the control plane, so things like max request in flight, so you get more throughput as you need it as the cluster scales. We also tune the QPS, so if your cluster needs to do more work, QPS for like the scheduler, the controller manager, things like that. If it needs to do more work, it can as it scales up. Also, due to the nature of long-lived connections within Kubernetes, we've implemented what we call go-away chance. It's part of Kubernetes. Effectively, what happens over time is these long-running connections cause traffic imbalance across instances. And so what we do is we randomly kill these connections, and what the clients do is they attempt to reconnect, and likely they will end up on a different API server. EKS tests, we make sure that we're scale testing all the time so that we're meeting or exceeding customer requirements. So we leverage the upstream CL2 framework to run our scale tests. We also make improvements to these CL2 tests based on things that we learn from our customers. For example, we recently added support for CRDs because there's actually a much larger penalty for listing CRDs versus listing things like pods. So we also have upstream 5K node tests running on AWS, and these today are release informing. So they sort of indicate to the upstream release team, whether there's any performance regressions or not. We test with real nodes, as in like real EC2 instances, and real customer workloads, instead of relying just on synthetic testing, which may or may not hide some issues. Finally, we're part of SIG scalability, where we're working on improving a lot of the SLOs that upstream has defined, and for things that you care about, things like pod launch latency, network connection latency, that kind of stuff. Okay, let's move on to etcd. So in a Kubernetes cluster, etcd is used to store all the config data for the cluster. This includes all the objects, things like pods, namespaces, and any other resource that you create within the cluster. It's a distributed key value store. It's a version-based system, so that it's not just storing the API object. It's storing every update as a revision to that object into the etcd cluster. Uses RAF for consensus, which requires 3 nodes to form a cluster and a minimum of 2 nodes to maintain the quorum. So RAF is kind of the secret behind etcd in providing fault tolerance and strong consistency. So RAF works by electing a leader and making sure that all writes go to the leader, and none of the followers can do it right. So it's designed to be highly available, and it's recommended for a small data set as opposed to other databases that can grow much larger. So why is etcd important to Kubernetes? It's kind of the essential piece behind Kubernetes for ensuring high availability and consistency of that cluster. It's crucial for maintaining the desired state and monitoring of changes, events that are happening, and it can also be used to help recover from a failure. It's probably the most important and most complicated piece within Kubernetes to operate. So within EKS, we run etcd as a 3-node cluster. EKS uses static IPs and static volumes. Static IPs for the networking, static volumes for the data storage. What we mean by that is the same IP and volume is used irrespective of if an instance fails. This is useful for durability as well as disaster recovery kind of scenarios. So etcd is fully managed within EKS. Not just the availability aspects, but all the maintenance aspects as well. Things like you have to compact over time. You have to defrag the cluster. All these things are done for you. We do them behind the scenes. We also right-size etcd, so the same scaling logic we talked about earlier, that applies to etcd as well. So we also take periodic backups, and these are stored in S3, encrypted. In the event that you need to restore from a backup or something really bad happens, we're able to do that. Okay, so in 2023, we moved etcd to static volumes. So there's a single volume per AZ, per cluster, and the lifetime of that volume is the lifetime of the cluster. So for example, if an instance in AZ1 were to fail and it gets replaced by another instance, the volume is moved to the new instance, and that instance joins as a follower to the cluster. In the event that we lose 2 out of 3 instances, or we lose quorum, we don't have to restore from a backup. We are able to effectively take the same volume and join the cluster and catch up. So this architecture also helps with the time to recovery. So as part of when a node joins a cluster, it has to do a snapshot transfer from a leader to the new node. This can take several minutes if it's like a, multi-gigabyte database. So with static volumes, one of the things that it gives us is we don't have to catch up from the beginning, from the leader. So this actually helps us, in the event of failures, recovery becomes much faster. Okay, so etcd, like I said earlier, it's designed for small data sets. By small, it's, 10 gigs, 12 gigs, that kind of thing. It's not super small, but because of that, there is a database size limit implemented in etcd. So one of the things we talked about earlier was that there's a separate revision for an object stored in etcd. So each time there's an update to the object, such as a status field changing, etcd is actually creating a copy of that entire object and storing it in its database. So it's not just new things like a pod getting created. It's everything that's happening. If there's a crash loop back off or something that lasts for an hour, every status change is going to result in an additional revision of that object. So that can also contribute to the database size itself. So when we hit the limit, etcd emits a no space alarm. It becomes read-only, and at that point, all requests to mutate objects are rejected. So the only thing at that point you can do is compact and defrag. And that's only going to help if it's the number of revisions that are causing the disk space to go up, right? If it's actual objects, defrag or compaction cannot help. So this year we added automatic recovery. So we have a new flow that we built where every so often when we get to that, close to that maximum database size, we accelerate the compaction and defrag that we do in the event that we can automatically recover the cluster. So if your cluster has a no space alarm, it can take up to 15 minutes, but if the recovery workflow can resolve it, it'll be out of alarm within 15 minutes. If it can't resolve it, it probably means you have to go delete objects to free up the space. Okay, oops. All right, so I want to go a little bit behind the scenes of how we release software. So things like platform versions that you see changing underneath. So we'll start with talking about kind of how we minimize impact on releases. So we're in every region today. Each region is split into cells. These cells are nothing but AWS accounts, and we distribute clusters across these cells. This isn't kind of a novel idea at all. It's any large-scale service probably follows a similar pattern. The important thing is we limit the number of clusters in a cell to effectively that contain our blast radius. So when things bad happen to a cell, we know that only that clusters in that cell will be impacted. So we have 1,000 clusters per cell, and we do progressive deployments, which we're going to talk about in a minute, to make sure that we're doing this all safely. So the way we release platform versions is obviously looks like something like this pipeline workflow. We do testing at various layers of the application. So things like individual components are tested. We have integration tests when they're all packaged together. And then finally, we do like an end-to-end cluster test. We also have a broad spectrum of tests that we run: conformance, version updates, platform version updates, and scalability performance tests that we run. And finally, there's testing that happens at every stage of the pipeline. So at beta, gamma, it happens in every region, and it happens prior to us promoting to the next stage. The scale of our fleet is pretty massive. We're talking about several hundreds of thousands of clusters. And these instances that are running these clusters, they need software such as OS patching or new versions of containers, new patch releases of Kubernetes. So our challenge is balancing safety with velocity, given the number of regions, number of cells that we're operating. So to hit the right balance, we've kind of sort of used deployment strategies that AWS has evolved over time. So we have bake times across each one of these waves. That bake time gradually decreases as we progress further in deployment. And then we also exponentially grow the number of waves, and at any point in time, we can do a rollback. So this is kind of the visual representation of how your clusters are receiving new platform versions, and without impact to anything, any of your workloads. Okay, so after operating EKS for 5 years, we've seen pretty much everything, the good, the bad, and we've converted a lot of these things into best practices. So I'm going to go talk through some of these. First, we'll talk about how things can go wrong. So using Kubernetes comes with kind of this shared responsibility to do certain things correct. It's really easy to misconfigure clusters, and sometimes this is due to kind of the vast ecosystem of software that you can install. Sometimes it's due to not knowing the best practices. So we've seen issues where customers have been negatively impacted by API priority and fairness, where critical workloads don't get through and causes some production impact. Another classic problem is webhooks, which are in the critical path of every request. So we see customers that don't properly configure webhooks, whether they're failing closed, they don't have enough replicas, they're not zonally redundant. So I'll give you some tips in the next slide, but we also have bad clients that have impacted the cluster itself. There's, the Kubernetes API has different ways that you can design good clients to leverage things like the cache, and not negatively cause load, unnecessary load on the API server. So we have a best practices guide that we've created. So it kind of just helps you think about and resolve for some of the things we talked about. So today you can monitor the API server with Prometheus, but this isn't enough. You should actually be looking at your audit logs. This is how we do debugging. We start with the audit logs. We have queries that tell us, okay, what are the most expensive calls? We figure out who the top talkers are by identifying the user agents or the clients that are making tons of calls. And this is what helps us narrow down whenever there's a problem. And you can do all this yourself if you have logging enabled. Preventing 429s. As of 1.25, a lot of the behavior in API priority and fairness has changed. So we recommend figuring out kind of what your call patterns are and fixing the flow schemas so that it's well suited for your applications. And then building well-behaved clients. So optimizing the API usage. So using things like watch, using paginated requests, eliminating things like cluster-wide list calls, querying by namespace, querying by field selectors. These are all ways that you're going to reduce the load on the cluster. Understanding your limits. So limits are everywhere in Kubernetes and in AWS for good reasons. We recommend sharding your applications to honor these limits. Things like limiting the number of objects in a single namespace, the number of load balancers in a single cluster, because you're going to eventually hit some other limit that will impact you. So, and finally, we recommend cleaning garbage collection. So things like cleaning up cron jobs by just simple things like using TTLs, deleting CRDs. So we've seen applications that use CRDs to maintain a lot of their event histories. And so, there's no good reason to do that. Go clean that up. So you can find out this and, some of the things I'm talking about, as well as many more things in the best practices guide that we have here. Okay, so finally, I want to talk a little bit about the community aspects. So all the work we do in EKS is in partnership with the community. So this year we migrated the upstream registry to registry.kh.io. This is running on ECR on AWS. We're part of the LTS working group, as Vipin mentioned. We're working to figure out what extended support, long-term support means. We have multiple members in the security committee. We've also moved a lot of the release-informing test infra jobs to AWS. And this goes along with our commitment to supporting the community with AWS credits. So there's a lot more we're also doing, KEPs, bug fixes. Our goal is to leverage kind of the operational muscle that we've built, managing these clusters to influence the upstream project. So with that, I'll hand it back over to Vipin.
Thanks, Vipul. So to wrap up, I'd like to go over a few things that have been keeping us busy. We are investing in solving the operational pain points of our customers. I hope you appreciate all of the undifferentiated heavy lifting that we are taking away with EKS, and we're continuing to do that. One of the areas we're looking at is to take on more add-on operational software that we can manage. We also heard from you that you want better visibility into cluster telemetry and observability. Vipul mentioned that a couple of slides earlier. So you've told us that you want to know what is going on inside the control plane, like better access to metrics and logs. Opinionated templates. We have folks at different stages of their Kubernetes journey in this room. Some of you have told us that you like to have the flexibility of tweaking the different knobs, but some of you have told us that you would like us to be opinionated and give you some templates with which you can launch a cluster. So we're trying to figure out what's the best way to deliver that to our customers. And we're constantly investing in improving the efficiency and fleet level operational work that we do for our cluster so that we can deliver a great experience to you, and you can in turn deliver a great experience to your end customers. So we have a public roadmap. It's on GitHub. Everything we do at AWS, including on our team at EKS, is based on what you tell us. We work backwards from what you tell us. So please, let us know through the GitHub roadmap as to what you'd like to see in EKS and how you'd like to see the future of EKS shape up. Thank you again. I hope you appreciate this session on how EKS works behind the scenes and all of the operational overhead that you would otherwise have to take on by self-managing your Kubernetes clusters. We have our LinkedIn profiles over there for myself and Vipul. Feel free to reach out to us on LinkedIn, and also please remember to give us some feedback on this session. Thank you again for joining us. Have a great rest of your conference. Thank you.